And you can see that this graph has a defining equation which distinguishes it from the previous two. All right, reading it, it would say the graph of y is equal to a times b to the exponent x. So I'm hoping that all of you are able to see that the x and the placement of the x makes this significantly different to the previous graph that we've been looking at, which was the hyperbola. So look at the placement of the x here. Here it was the denominator. Here the x is elevated and it's actually the exponent. So the first thing is that we call this graph the exponential graph. It is an exponential graph purely because the x variable is in the exponent. All right, it says, it should be noted that this graph will only have a horizontal asymptote, and it should be noted that b is greater than 0. Well, let's have a look in application what those two notes are actually asking us to commit to our memory. And of course, the best way is with an example, and we're going to take an example as it appears in your workbook, and it is on page 125, right up at the top. Okay, look at the graph of y equals 2 times a half to the x. Now, can you see that our original defining equation said that an exponential graph is that one that has of the form a number a times a number b to the power of x. Now, that is why this is qualifying. Can you see that in this particular given equation, our a value is in fact a 2, and our b value is in fact a half, and x is our exponent. Now, how on earth do we get from this, our defining equation, to this graph here that we have in front of us? And of course, guys, again, if we're going to draw a graph, the best way to actually start off any graph is to take the equation and to see what happens when we plug in x values and see what kind of a y value that creates for ourselves. So let's take x to be a 0. So we want to know what is the graph doing when x is 0, in other words, on the y-axis. Now, clearly, I'm going to get my y value to be 2 times a half to the exponent 0. Now, I'm hoping that you guys remember that anything to the power of 0 is equal to 1. So this becomes 2 times 1, which is 2. So as a result of that, I know that my graph must go through a point 0 and 2. So I can plot one point of my graph already. Now let's take x as a positive number. So if I take x to be 1, my y will be 2 times a half to the exponent 1. Right, now going through your exponential laws, a half to the power of 1 is a half. 2 times a half is 1. So that is telling me that when my x value is a 1, my y value is correspondingly 1. So I've got those 2 points plotted already. Is it enough? Definitely not, because you might then go shooting up to the sky. We really want to see why this graph comes down, and can you see that it's approaching the x-axis, which is what they were talking about as the x-axis being a horizontal asymptote. Again, that plane is coming into land, but it's never, ever, ever going to get there. So I'm now saying, let's find another value for x, and I'm going to say, let's move across and say, what is happening when x is 4? So my y value is going to be 2 times a half to the 4. Right, now, a half to the 4 is going to be 1 over 2 to the 4 is 16. 2 times a 16th is an 8th. So my point is going to have to be 4 1/8. And can you see that the 1/8 is ever so slightly above the x-axis? Okay, but it is still above the x-axis. My next points are going to be a 16th, a 32nd, a 64th, and so on. And it's going to get smaller and smaller and smaller, but it's never going to touch. Right, what's going to happen on the left-hand side of the graph? Well, let's see what happens at -1. So if we just pop in x is -1, we're going to get y to be 2 times the half to the -1. All right, so again, unfortunately, maths is made of building blocks, so we need to realize that a half to the -1 is the same as 2. And so 2 times 2 is 4. So this is telling me that the point -1, 4 has to lie on my graph. And that would be good enough for me as your teacher, because you could now join those up and you can see that what you've got is a new kind of graph. It's very different to the parabola. It's very different to the hyperbola, because can you see it's going through a point on the y-axis? The hyperbola didn't. All right? And then you can see that what it's doing is it's climbing up as high as it needs to, but it's also coming down and it's asymptotic to the x-axis. So what we need to remark about here is that we definitely have an asymptote. And this asymptote in this particular graph is going to be the line y equals 0 or the x-axis. Right? Let's now just make some kind of a note about the domain of this graph. All right, now I want you to think, when I was choosing values for x, I chose some positive values, I chose a negative value, I could have gone on and chosen more positive or more negative, and I would have gotten answer every time. So in fact, my domain is x can be anything it wants, positive or negative. But my range, right, remember my technique for range is I'm coming up from below. Am I getting a line that hits my graph? Definitely not. So where do I start getting y values living on my graph? It's at the x-axis and then anything above. So that means that my range is definitely going to be any y value, all right, that is greater than 0. All right, please do not write y greater or equal to 0, because we can't let it be 0. That's where the asymptote is. So it must be that your range is your y values are greater than 0. Of course, if you put it in interval notation, you would say from 0 up to infinity. Okay, so that's been your first experience of an exponential graph. Let's move to a second one and see if you're as good as I think you are at this point in time. So we're now on page 125 in the middle, and we're looking at the graph of y equals 3/2 to the exponent x. Now remember, our defining equation should be a times b to the exponent x. So now you're saying, but where's the a? Of course it's there. It's just an invisible one. So it definitely fits the mold, and the thing that's screaming at me is that that's what tells me it's an exponential graph. So I'm expecting it to be asymptotic to the x-axis in this particular case, and then I'm expecting it to actually do some kind of a movement. Now, can you see that the last one, once we'd finished it, it kind of started up at the top left and it decreased, and then it headed for the x-axis over here on the right. Now this one is different. Can you see that instead of it starting up here and coming down, it actually starts down at the bottom and increases, crosses the y-axis, and then keeps on increasing. Now the difference, if you recall, the last equation had a defining equation that looked like this, and our one this time is y equals 3/2 to the x. And the big difference, and we need to recognize this from the start, is in this one our b value is 1/2, and in this one our b value is 3/2. So now you're saying, so what? They're both positive. Yes, they are. They have to be both positive. But this one is greater than 1. Now, if something is greater than 1 and we raise it to an exponent, what happens is that it gets bigger. So it's going to increase, get bigger. But this one is going to actually be less than 1. It's positive, but it's less than 1. And as we take something like 1/2 and we make this value get bigger, this number actually gets smaller. So that's how we check. If this number here lies between 0 and 1, all right, my graph is going to get smaller, decrease. If this number is bigger than 1, my graph is going to increase. And having said that, really that would have become clear if we had just taken the time and gone off and plotted in some points. So we've got our equation as y equals 3/2 to the x. So you're getting used to this now. If x is 0, our y value would be 3/2 to the 0, which is 1, which gives me a good point to plot. If x was 1, my y value would be 3/2 to the 1, which is just 1.5. So at 1, I go and plot 1.5. I can see that it's increasing. I know that that's going to be the further trend. So I'm going to now take x being a -1. And of course, my y value would be 3/2 to the -1. We know that that flips the number, so it would become 2/3. So at -1, I would have to plot 2/3. And I can see that what I'm going to do now is just join them up. So what kind of comment would you now be making? I'm hoping that with repetition you are now saying, that's good, that's what my graph looks like, but what would my domain be? Well, my domain is definitely any value for x, positive or negative. What would my range be? And again, guys, I'm hoping that you're now saying that y is going to be greater than 0. Again, can you see? It's asymptotic with the x-axis coming over here to the left, but we could have any positive value that we wanted for our range. The other words that I've used is I've said to you that this graph here is actually an increasing graph. Okay, whereas just let's look at that previous one and get a full frame. We use the language that this graph here would actually be a decreasing graph. And again, our gremlins have kind of crept into our printing. In your book, this reads a minus sign. So in your book, it says y minus 1/2 in brackets times 4 to the x. So please, could you just take out some kind of a color and just make sure that you change that minus into an equal sign. So y is equal to 1/2 times 4 to the x. So, candidates for 6 marks, please draw this graph. So the first thing that you as the learner are going to do, you are going to say, what format is it? And can you see that it's very definitely of the form some number times another to the x. Now, if we have a look at my b value, it is a 4. Not the a value, the b value. So the thing that's been raised to the power. It is a 4. And so I am thinking that because my b value is bigger than 1, my graph is going to be an increasing graph. Okay. I don't get any marks for this, by the way, but what I'm doing is I'm just kind of programming my brain to expect the right graph when I draw it. Okay? I'm going to go and I'm going to actually put these values into my calculator. Right, so we are going to say that our function, We're just going to clear that off quickly. Our function is going to be our new one that we have been given, and it told us that it is going to be a half. All right, and then it's 4 to the exponent x. All right, I've taken the time to do this on the calculator purely so that you can see that I must put those brackets in there because the x needs to just raise the power of 4. Equals. I'm only going to start at -2. I'm going to end at 2, and I'm going to go in steps of 1. So what I now have on the calculator is exactly the same as in your table in your book. So -2 minus 1, 0, and if we go down, we land up with the values for 0, 1, and 2. Right, so you now believe me that that's what our calculator would look like if we were to draw the graph, and so let's just plot those points in. All right, -1 has to be with 0,125. Now that's an eighth. All right, so I kind of come in and I'm very close. 0 has to be with a half. 1 needs to be mapped with 2. And 2 needs to be mapped with 8 up here somewhere. And of course what you would then do is you would take your very steady, sober hand and you would draw in your graph. Now you can see that at the end here I actually have committed a sin, because can you see how my graph kind of started taking off again, which is not great. I must make sure that I'm kind of bringing it in ever so close to that asymptote, which as you can see is quite difficult. Okay, so guys, what did they ask us to do? They said that we needed to draw y equals a half times 4 to the x, and we have convincingly done that. Of course, if I was your teacher and I was awarding marks for this, I would want you to label it. So I would put a half times 4 to the x. Then obviously I could ask you some questions about the domain, the range. My asymptote is again the x-axis. You can see that it is again an increasing graph, and that has been brought about purely by the fact that your b value, your base that was being raised to the exponent, was a number that was bigger than 1. Okay, what we're now going to challenge you with is quite a nice exercise. What we're given in each case is an axis, and then there are 2 graphs. And we need to take the 2 equations and we need to match them. So starting off with the first one, we're on page 126 in the middle, example 1. It gives us 2 equations. Y is equal to 3/4 times 2 to the x, and y equals 3 to the x. Both of them are exponential, as we can see in the picture. So we can't distinguish them because one's parabolic and one's hyperbolic, but they're definitely both exponential. Can you see that's positive? That's positive. So both of them are increasing, but we need to identify which is which. Now, I find the easiest way to identify is to actually have a look at one value for x, and I'm going to take x to be a 0. Now, if we take x to be a 0 with this one, can you see that your y value would be 3 to the 0, which is 1. So we would know that this graph goes through 0, 1. Likewise, if we took this one and we let x be a 0, we would get our y value being 3/4 times 2 to the 0. 2 to the 0 is 1. So 3/4 times 1 is 3/4. And I think you can see that we've actually put this one to bed already, because this yellow must go through 0 3/4. All right? That's it. That's the point 0 and 3/4. This white one must go through the point 0, 1. So everything else follows. So this solid line graph is definitely y equals 3/4 times 2 to the x. And the dotted line graph, by comparison, is the y equals 3 to the x. How easy was that? I'm sure you thought that it was quite hard before we started, but really what we just have to do is match one of the points on the graph and see how it aligns itself with the given equations. Okay, so let's move on to 1.2, same page, and see if it's as simple. So here what we have, guys, is y equals minus 2x squared and y equals minus a half x squared. So now you're thinking, these are both parabolas because of the defining equation. Yes, they are. They both sad parabolas. All right, so that's why both of them are negative. But now, which one is which? Now, if we were to take x is 0, can you see that by feeding a 0 in there, we get y to be 0? So this is telling me that this graph goes through 0, 0. All right, well, that's not much help because you can see that on the other side, if I let x be 0, y is also 0. So after that little bit of effort, I've confirmed that both of them go through the origin, which is what we know for our particular parabolas. So let's find another point. So I'm going to say x is 1. Notice that x is 1, my y value comes out being at negative a half. 1 squared is 1 times negative a half. Here, if x is 1, my y value comes out being negative 2. So can you see where I'm going with this? 1, negative 2. 1, negative 2. So that point lies on that graph. Whereas the point 1, negative a half, all right, which is there, lies on that graph. So can you see that I can quite cleverly now say that y equals negative a half x squared is going to be the dotted line, and by comparison y, I don't want to write it there, I want to write it here, y equals minus 2x squared is going to be this solid line. And I'm not sure if you remember when we were doing the parabolas, we said that the bigger this number, the narrower or skinnier the graph, and if this number is small, like a half or a quarter or even something like 3/4, then my graph is fatter. So you could even have identified these graphs just by whether it was skinny or fat. So this one we know is going to be the skinny chap, and this one is going to be the fatter or the wider. Okay, let's move on to the third one as our third challenge in this particular exercise, and you are working with me along on page 127. So we've got y equals 2 over x. We recognize that that is a hyperbola, and y equals 6 over x, also a hyperbola. Okay, guys, so what I'm going to do is I'm going to have a look at what happens if I put x is perhaps a 6 into this particular equation. I've chosen that because I know a factor of 6 is 6. So plugging a 6 into there, I get my y value to be a 1. Now notice that there sits beautifully my point with coordinates 6 and 1. Let's try on the other side. We've got here, let's say x being a 2, chosen again because 2 is there. Then I'm going to get my y value to be 2 over 2, which is 1. And you can see that that lands up being that point. So I don't have to check anything else. I know that this one is going to be y equals 6 over x. And I know that this one here is going to be y equals 2 over x. Now remember that this guy is twinned with its mirror image over here in the third quadrant, and so is this. So you don't have to check anything else. because this equation actually is the kind of description for both dotted lines, and this equation is the description for both solid lines. Just one thing I want to point out for you. Can you see that with them drawn on the same axis, can you see that when the A value is small, you've got quite a scoopy hyperbola, and when your A value is big, it's just strung out a little bit. It's just a bit tighter. So I'm hoping that you would be able to kind of think that if I had something like a 10 over x, all right, what do you suspect is going to happen there? It's just going to be strung even tighter somewhere here in your first quadrant. Okay, I'm hoping that you are excited by what we're doing here, because it's really pulling everything together, and we're now on exercise 1.4 of page 127. So it tells us that the two graphs that we're actually looking at here are minus 2 tan x and minus 3 tan x. So both of them are negative. All right? The one has got a 2, the other one's got a 3, and they're both tan x's. So how do we work out which is which? Now, do you remember that with the tan graph, the thing that was important was what was happening at 45. So in the normal tan graph, it would go through 45 and 1. This would be in normal tan x. All right? Likewise, if we took 2 tan x, it would be going through 45 and 2. Now, that's a positive 1 and a positive 2. They are talking about a negative 2 and a negative 3. So I'm going to check what's happening at negative 45 over here. Now, negative 45, if I move up, hits this solid graph at 2. So this is the point, negative 45 with 2. All right, using exactly the same line of thought at negative 45, if I keep on going, it hits the dotted graph at 3. And guys, that's it. That's all that you need to do to distinguish between the two graphs. So the one that's going through negative 45 with 2 is going to be this one, y equals negative 2 tan x. So my solid one is y equals negative 2 tan x. Right? And my dotted one, because the dotted one was paired with negative 45 and 3, this one is going to be y equals negative 3 tan x. Now, you don't have to do any more work than that. Clearly, each of these would be out of perhaps 1 or 2 marks, and your teacher is just trying to see, do you know what effect this parameter minus 2 has had on the graph and minus 3 has had on the graph? And can you distinguish what makes them different in their actual drawing of the graphs themselves? Okay, moving on to the next example, which is now number 2 on the same page. It's page 127. All right, it's no longer giving us 2 graphs and telling us identify which is which. It's got something a little bit different. It says the graphs of y equals a half to the x and y equals minus 2 over x are sketched. And this is something new. It's only sketching them for x less than or equal to 0. So before we go charging into the actual questions, let's analyze the kind of wealth of information that we've got here. We've got a graph of a half to the x. Now, my first train of thought is to say, which family of graphs does that fit into? And because it's got an x, I'm thinking to myself that this is the exponential. Right? So, unlike the previous question where they were both exponential or both hyperbolic, here we've got one that is exponential, and then we've got the other one, which is y equals minus 2 over x. And again, I ask myself, what is that one? And we know that this is the hyperbola. So having said that, what else is different? Well, they've only given me a snapshot of the x-axis where the x values are negative. So in other words, my domain is not reals. I'm not working right the way across. I'm only working with this limited x to the left of the y-axis. Okay, let's have a look at what they want us to do with this. It says, write down the coordinates of the point of intersection of the two graphs. Well, I don't think that that's going to be too major because it just says write down. So I must be able to go to my picture and from my picture read off where the graphs meet each other. So that means that point there. All right? So what are the coordinates for the point of intersection? We can see -1 and 2. All right. And again, I say to you that those are marks that are meant to be achieved by every candidate who writes this test because it's really not difficult. The only thing is, do you know what intersection means? Right, the next question. Write down the range of the exponential graph, but now notice that they've given it to you again within this limited domain. Okay, so what is our range of our exponential graph? Now let's just make sure that we understand that this is our exponential graph here, and where normally it would have gone on there, we can't see that bit. Okay, so it's our decreasing function, but we can't see how it extends and comes in asymptotic to the x-axis. So what is our range going to be? Now remember, our range is our y values. So using my method, I'm saying, can my y values actually be between 0 and 1? Only if the other part of the graph was there, but it's not. So the first point where y actually takes a value is when y is 1, and then thereafter the y values can increase at liberty. So can you see that this is a little bit different? It's going to be our range must go from 1 only up to infinity. So how would we write that down? We would actually say 2.2, our y value must be greater or equal to 1. Y is an element of real. Or alternatively, in interval notation, we'd say from 1 up to infinity. Okay, that having been achieved, we can now do 2.3. Write down the equation of the reflection of y equals -2 over x for x less than 0 in the y-axis. Now, can you see that they're not allowed to put the bar there? Because remember, this is a hyperbola and x cannot be 0 because then you are working with an undefined value. So they cannot put the bar there, which is why we're now going to have to remove it to replace it to what it was in the original question. So write down the equation of the reflection of our hyperbola in the y-axis. Right. So here we have our hyperbola. They want us to reflect it in the y-axis. So let's have a look at what that would look like. So if I reflected this point, for example, it would land up there. If I reflected this point, it would end up there. This point would reflect to there, and likewise, if I kept on going, I would get a graph which looks something like this, if I reflected it in the y-axis. Now, what is the equation of that reflection? Well, I know that we come to do a section later on in our workbook on reflections. But let's just take one point and see what's happened. Right, this point, for argument's sake, is going to be -1 and 2. Once I reflect it, are you comfortable with me saying that this would reflect 1 unit across, so it would become the point 1 and 2? So the reflection has meant that the y value has stayed the same, but the x value has changed its sign and become a positive 1. Okay? Now, do you remember that when we had a hyperbola, anything that was negative over x landed up here and here. Anything that was positive landed up in the first quadrant and the third quadrant. So what we now need to see is that our equation as it is at the moment is y is equal to negative 2 over x. So y is equal to negative 2 over x. All right? Now there's two ways to go from here. We can either say we know that in the reflection the x must change sign. All right? Which actually means that I'm going to come down here and my new equation is going to be minus 2. And then watch how natty this is. My x must change sign. And so I now get a minus divided by a minus is a plus. And so the equation of my reflection is going to be 2 over x. Okay? So what that means is that where this one was minus 2 over x, by changing the x's sign, we've landed up with this dotted one landing up in positive 2 over x. So I said that there were two methods. So the one method is knowing that the x must change sign. Our other method is actually just knowing that at the moment my graph is here because my a value is negative. Okay, so I'm saying that this is because my a value is negative. If I want this one, on the other hand, I know that anything with a positive value is going to have to be a positive over x. So intuitively, if this was negative 2 over x, this one would have to be positive 2 over x. All right, the last part of this question says, write down the equations of the asymptotes of y is equal to minus 2 over x for x being negative. So again, we go back and they want us to have a look again at the hyperbola and they want us to define the asymptotes. Well, can you see that as this one comes into land here, it cannot land on the x-axis, so that is an asymptote. And it cannot go across the y-axis, so that is an asymptote. But now I just caution you, because they said they wanted the equations of the asymptotes. Now, yes, the x-axis and the y-axis are the actual lines, but the x-axis has the equation y equals 0, and the y-axis has the equation x equals 0. So would we penalize you? Well, then very definitely we would, because the question specifically says write down the equations of the asymptotes. So if you just said x-axis and y-axis, although they are the self-same line, we need to answer the question in the format that they've actually asked us for. It says, the graphs of y equals tan x and y equals a sin x are drawn below, and it tells us that the actual area or the domain that they've drawn specifically for is going from minus 45 over here, just beyond the origin. So let's just identify the origin there for you. And the graph is drawn all the way up to 360. And in fact, these bits here shouldn't be there if we are being pedantic. Okay, the question says, write down the value of A. So now you scratch your head and you say, well, which A? All right, where is A? What are they talking about? Well, if we go back to our defining equation, can you see that they gave us y is tan x? So the graph that we've got drawn here is definitely tan x, plain simple tan x. But they gave us a kind of a mystery value for a in front of the sin x. And we have to go to our graph and we have to see, kind of solve the mystery as to what that value of a would need to be so that it matches the picture. So let's look at sin x. We know sin normally starts at 0 at the origin. Normally in the plain simple sine it goes up to 1 at 90. Can you see that this guy is actually going up to 2? So what has happened is that the amplitude has been stretched, and this point here is now a peak or a maximum at 90 and 2. And the only way that that could have come about is if that a value there happened to be a 2. Okay? Now it says, show on your graph where you would read off the solutions to tan x equals a sin x. Now notice you have actually worked out the value of a. So going forward you can imagine that that there says a 2. If you hadn't been able to work out a, it makes no difference. You would still be able to follow the instruction which says, where would you read off the solutions? Not what are the solutions, where would you read off where the one graph equals the other? And we know that where graphs are equal, that's where they meet. Where graphs meet or intersect, all right, that is going to be here. All right, here they meet. They actually meet there. And they meet here. Now, it says show where you would read off the solutions. Now, I don't know about you, but if you just did that, all right, your teacher actually doesn't know what you intend for those blotches. So what would be a good idea is you could put a value there, and notice a is on the x-axis. Then you would actually say, well, I would read off their B place of meeting there. I would read off their C place of meeting correctly there. And my D place of intersection here. And then I would just kind of be over emphatic and I would say, they meet at A, B, C, and D. Okay, so moving on to 3.3 of the question, we changed gear. They've been asking us about the amplitude. Now they want us to focus on the period. So write down the period of the graph for sine. Now, even although you've drawn it from -45 all the way to 360, we've actually gone beyond where one pattern would have happened. So can you see that the period of the up bump and the down bump is it's taken 360 degrees to complete its course. So we are going to not be fooled by that little extra bit tacked onto the left-hand side. We are just going to say that the period is 360 degrees. And lastly, 3.4 says, write down the range of y equal to tan x. Now this one you should know with your eyes closed, but we know that our tan graph is going to head all the way down. It's actually going to head for the skies as well. There's no limit or any kind of a barrier. And so we know that the tan graph is actually going to have a range which is unlimited. All right, and so we know that our range is y, element of real, or alternatively we could say y goes from negative infinity all the way up to infinity. Now I'm hoping that you're looking at this question and saying, well, if that's the level of question we're going to be getting in our tests, well then I'm going to wax this, because what more can we have explained to have actually got you to understand the 4 easy questions that they've actually asked. It's just for you to change gears and to say, what is it that they're actually asking me here?